Okay, so today we're going to be talking about rates of change. Now, what a rate of change really is just comparing the change in one variable to another variable, to the change in another variable. So it's like saying that the change in y over the change in x. That's the simplest way to put it. Now, what we've always done from in high school is talk about the average rate of change. What that is you're taking two different points, say here and here, and you're figuring out the average change, rate of change between these 2 points. So you're taking the change in y, and you're taking the change in x, and you're putting them over each other to figure out the average rate of change. Now if you look here, you can see like that's a straight line going here. The actual function might curve up, but that's not what we're talking about. We're talking about the average rate of change, so we're just getting the straight line from this point to this point. And that's represented in this equation. The change in y over the change in x, or f of x1 minus f of x0 all over x1 minus x0. But now that we know calculus and we know limits, we're able to find something else, which is the instantaneous rate of change, which isn't the change between 2 points. It's the rate of change at one specific point. And the way we do this is we take the equations we had before for the average rate of change, and then we use those and find the limit when the difference between the 2 points becomes 0. So where the space between these 2 points, where the x difference between these 2 points is a certain value right now, we try to get it to as close together as possible so that you can basically say that there's no space between, and so that we can say we found the instantaneous rate of change. Or other words, another word for this is the slope. See here we found the slope between these 2 points, but we're doing with the instantaneous rate of change, we're finding the slope of a tangent line at a specific point. Now when you're solving these equations, there are 3 steps you have to follow. Or not necessarily follow, but it's good to be aware of. The first step you should take is to figure out what equation you're using when you do these questions. So a rate of change question normally asks something like, what is the instantaneous rate of change of the volume of a cube or of a cylinder with respect to something? And when asked that, you have to figure out the equation that it's talking about, because it doesn't always explicitly tell you what the equation is. You have to figure it out yourself. So that's the first step. And once you figured out the equation, what you then have to do is find the derivative of it, because what we're doing is, since we're finding the slope at some specific point of this function, that's essentially what a derivative is. That's what we've learned already in this class, is that a derivative is a way to find the slope of a function. So if you take the second step, which is just find the derivative, and that derivative is with respect to x, or whatever the variable is you're using in the equation. The third step then, after that, is to plug in your a into the derivative. And what this means is that normally in the question, it will ask what's the instantaneous rate of change when s equals 4 or when x equals 9. So it's giving you a point to find that instantaneous rate of change, and so you just have to plug this into your derivative, because your derivative is the equation to find the slope, and you're plugging in your value, which is going to be the slope at that value. So those are the 3 steps to follow. And to understand this, we can look at some examples. So if we look at this first question, it's an easy one. Find the instantaneous rate of change of the volume of a cube with respect to its side s, when s equals 5. So it's asking us to find the specific rate of change at point 5 with this equation. So if we follow the steps, the first step is to figure out what the equation is that we're talking about. And so it's talking about the change of a volume of a cube with respect to its side. So we have to find an equation that has both volume and side in it, side length. So an easy one for that, it's pretty straightforward, is that the volume is equal to the side length cubed. So that's good. So we can move on, now that we know the equation we're talking about, we can move on to the second step, which is then to just find the derivative of this equation with respect to s. So we find dv ds is equal to the derivative with respect to s of s cubed. And if you just remember your power rule, that becomes 3s squared, taking it down and minusing 1. So that is now our derivative equation, 3s squared. And so the final step is now just to plug in our point, 5, into this derivative to figure out the instantaneous rate of change. So it's going to be dv ds when s equals 5 is equal to 3 5 squared. And that ends up just coming to 75 because 5 squared is 25 times 3. So you end up getting 75. And then you have to consider the units. In this case, we're talking about the volume with respect to the side. And so volume is measured in whatever you're talking about cubed. So like in this case, we're talking about meters. Say meters cubed is volume. And then length is just measured in meters. So what this is saying is that for every increase of 1 meter on the side length, it causes an increase of 75 meters cubed to the volume. And the meters actually cancel out here, so you end up getting the increase, the rate of change is 75 meters squared. It's important to remember that this is only at the point 5. It isn't always true for this cube. It's only when, this is the only rate of change when x equals 5 or s equals 5. So moving on to a slightly harder example, we have the volume V of a cylinder with respect to radius r if the height is equal to the radius. So again, we have to find the rate of change, but you notice a couple unique things about this question. First of all, it doesn't give us a specific point like the last one did. And what that means is that we're not finding the instantaneous rate of change at a specific point. All we have to do here is find the derivative so that we have the equation for in general for the rate of change. That means you only have to do the first 2 steps. The second thing to notice is this last sentence is if the height is equal to the radius. And that will make more sense once we start doing the question. So if we take the first step, finding what equation we're using, we have to look at, we're talking about the volume of a cylinder, and we're talking about the radius. And so an equation that has these in it is that the volume of a cylinder is equal to pi of the radius squared times by the height of the cylinder. And then now this is where the height is equal to the radius comes in, because if we just took this first equation and tried to find the derivative, we have 3 variables, so we wouldn't be able to do anything. So what we have to do is plug in r is equal to h because the height is equal to the radius, and so we can replace h with r because we're finding with respect to radius. So then we can just get this, the volume is equal to pi r squared times r, and we've put that together, so the volume is equal to pi r cubed. So that's the first step. We have the equation done. And move on to the second step, which is to find the derivative of this equation. We can take the dv dr of d with respect to radius of pi r cubed, which then, if you remember the power rule, and remember that pi is a constant, you move 3 in front, you get 3 pi r squared. So dv dr is equal to 3 pi r squared. So the equation for the rate of change of the volume of a cylinder with respect to r is 3 pi r squared. So now that we have this equation, if we wanted to, we could plug in any value into r and figure out what the instantaneous rate of change is at that point. But for this question, we don't have to because it's only asking for this equation.